Bismillahirrahmanirrahim. I am Dr. Javed Ali, Assistant Professor, Department of Chemistry, Cust. Welcome to the course Physical Chemistry 2. Course code is 332. Today's topic is kinetics of first order reaction. Outline of the topic: Introduction to first order reaction kinetics, mathematical equation and data interpretation. Examples of first order reactions. In first order reaction, rate of reaction is proportional to concentration of only one reactant. First order reaction can be represented as reactant is going to the product. A represent the concentration of reactant, P represent concentration of product. The rate law for first order reaction is dP divided by dt is equal to K a power 1, where P represent concentration of product, K is rate constant, A is concentration of reactant. dP divided by dt is rate of formation of product or change in a concentration of product with respect to T. We can also represent first order equation as minus dA divided by dt is equal to K power 1, where A represent concentration of reactant, K represent rate constant, and minus dA divided by dt represents change in a concentration of reactant with respect to time. And the minus sign represents the decrease in a concentration of reactant. So minus dA divided by dt represents the disappearance of reactant with respect to time. This equation represents that the rate of reaction is proportional to the concentration of the reactant. So we know the differential equation of first order reaction is minus dA divided by dt is equal to K a power 1, where A is concentration of reactant, T is time, and K is rate constant. We can rearrange this equation. Minus dA divided by dt is equal to K a power 1 by rearranging minus dA divided by A is equal to K dt. Now to convert this equation into integrated form, we need to take integration of this equation. By taking integration, we get this equation. Minus integration dA divided by A is equal to integration K into dt. We know K is constant, so we can take out K from integration. So now the equation is minus integration dA divided by A is equal to K integration dt. Integration of dA divided by A is equal to log A. So minus integration dA divided by A is equal to minus log A. And integration of dt is equal to T. So the equation become minus log A is equal to KT plus Z, where Z is integration constant, The value of z can be determined by putting value of a is equal to a naught at t0. So the z value is minus log a naught by putting t is equal to 0 and a is equal to a naught. By putting value of z, we get this equation. Minus log a is equal to kt minus log a naught. Minus log a naught is value of z. We can just multiply minus 1 with both sides, so we can get this equation. Log a is equal to minus kt plus log a naught. This is a very important equation for first order kinetics, where log a is variable and t is variable, where log a naught is intercept, k is slope, and this is straight line equation. If we plot log a versus t, we will get a straight line with negative slope. We can simplify this equation by taking anti-log. So now the equation is a is equal to a naught e power minus kt. This is another form of first order kinetics. We can also rearrange minus a is equal to kt minus log a naught. By multiplying minus 1 with both sides, we get log a is equal to log a naught minus kt. This is also a very important form of first order kinetics, where log a is dependent variable and t is independent variable, and log a naught is constant and k is constant. So this is straight line equation. We can plot log a on y-axis and t on x-axis. We will get a straight line equation with negative slope. With the help of this equation, we can determine, by plotting log a versus t, we can determine either this reaction is first order kinetics or not. We can also rearrange this equation by shifting minus log a naught to this side. The equation will become log a naught minus log a is equal to kt. This is another form of first order kinetics. We can further simplify this equation because we know log a naught minus log a is equal to log a naught divided by a. So the equation is now log a naught divided by a is equal to kt. This is another form of first order kinetics, and this is also a straight line equation. We can plot log a naught divided by a versus t, and we will get a straight line equation with positive slope and with no intercept. So these are different form of first order reaction. Graph. We can plot the first order kinetics by plotting log reactant concentration versus t. We will get a straight line equation with negative slope, and this represents log r naught or log a naught. And similarly, the rearranged form, we can plot log a naught divided by a versus t, and we will get a straight line equation with positive slope and no intercept. If we plot log a versus t and get a straight line equation with negative intercept, it means this is first order reaction. And similarly, if we plot log a naught divided by a versus t and get a straight line equation with positive slope and no intercept, it is also a first order reaction. So we can determine the order of reaction by plotting log R versus T or log A naught divided by A versus T. As we know, the integrated equation of first order kinetics is log A naught divided by A is equal to KT. As we know that the half-life can define as the time required for reducing the reactant concentration to half of its original initial concentration. So we can determine the half-life of first order reaction by putting A is equal to 0.5 A naught. By putting the value of A and T, log A naught divided by 0.5 A naught is equal to K, and T half represents the half-life. Now A and A will cancel with each other, and 1 divided by 0.5 is equal to 2. So the equation is now log 2 is equal to K and half-life. We can rearrange this equation as K half-life is equal to log 2. We know that log 2 is equal to 0.693. So K and T half is equal to 0.693. And half-life is equal to 0.693 divided by K. This is a very important equation. This equation shows that the half-life of first order reaction is independent of initial concentration of the reactants. This means that the half-life is only dependent on K and is independent of initial concentration, which suggests that the half-life of first order reaction will constant throughout the reaction. So with help of this equation we can determine either this is first order reaction or not. When the half-life remain constant throughout the reaction, this means the reaction is following first order kinetics. With the help of this equation, we can also determine the half-life of reaction if we know the rate constant. And similarly, we can also determine rate constant if we know the half-life. For example, if a K is 0.1 per second for a chemical reaction, we can determine the half-life for that reaction as well. As we know, half-life is equal to 0.693 divided by K. So by putting K value, we can calculate the half-life for that particular reaction. So half-life is equal to 0.693 divided by 0.1 per second. 0.1 is rate constant value. So by solving this equation, we get half-life is equal to 6.93 seconds. So with the help of this equation, if we know rate constant, we can calculate half-life for that particular reaction. Similarly, if we know the half-life for a reaction, we can determine or calculate the rate constant with the help of this equation. As we know, if the half-life for a reaction is 3.45 seconds, So by putting the value of half-life in this equation, we get K is equal to 0.693 divided by 3.54 seconds, where 3.45 second is value of half-life. So by solving this equation, we get rate constant is equal to 0.2 per seconds. So this equation is very important equation. With the help of this equation, we can determine the rate constant. If we know the half-life, we can also determine the half-life if we know the K. And with the help of this equation, we can also determine either the reaction is first order or not. Example of first order reaction: decomposition of hydrogen peroxide to H2O and oxygen is example of first order reaction. Similarly, the disintegration of uranium-238 to thorium-234 an alpha particle is also example of first order kinetics. Summary of today's lecture: rate of reaction is proportional to the concentration of reactant. The rate constant unit is per time, means per second or per minute or per hour. Depend on in which unit you represent the time. The half-life of reaction is independent of initial concentration of the reactant. The integrated equation for first order reaction is log A is equal to log A naught minus KT, where A is concentration of reactant at any T, where A naught is initial concentration of reactant. K is rate constant, T is time. We can also rearrange this equation to another form as log A naught divided by A is equal to KT. These are very important equations. We can determine the concentration of reactant at any T if we know the initial concentration and if we know the rate constant. By putting the value of initial concentration, rate constant, in T, the time at which the concentration of reactants are required. Similarly, if we know the initial concentration of reactant and we know or can determine the concentration of reactant at any T, we can calculate the rate constant. So these are very important equation. With the help of this equation, we can determine the reactant concentration at any T. We can also determine the T for specific reactant concentration. Furthermore, we can also determine rate constant from this equation if we know the initial concentration and concentration of reactant at any T. From this equation, we can also predict or determine the concentration of the product, because once we determine the concentration of reactant at any T, we know X is equal to A naught minus A, and X is equal to concentration of product. So we can also determine the concentration of product from this equation. With the help of this equation, we can determine either this reaction is following first order kinetics or not. simply by plotting log A versus T. If we get a straight line equation with negative slope, this means this reaction is following first order kinetics, and the log A naught will be intrinsic for that graph. And by another way, if we plot log A naught divided by A versus T and get a straight line equation with positive constant slope, it means this reaction is also following the first order kinetics. By using and plotting any method, we can determine either this one is first order reaction or not. These are some references for today's lecture. And at the end, thank you very much.